Thank you for the introduction. Good morning, everyone. I'm glad to be here, and thanks for coming. So I'm going to talk about text summarization and categorization in scientific and health-related data. So we all know that there is an increasing demand for use of health-related data. These include all sorts of information, from scientific papers and literature to social media data to clinical notes and patient reports. I'm going to talk about some of the works that we did that are about text categorization and summarization that can benefit some of the challenges in these areas. So in first part, I'm going to talk about scientific literature, and then I'm going to switch focus in second part on the works that we did in social media. And I'm going to touch on some of other works that we did that are about clinical data. So we all know that there is an increasing rate at which papers are being published. So it is ideal for researchers to be able to understand the papers or get the key contributions of the paper without the need to going and reading the entire paper. So this is a problem of scientific text summarization, where given a report, we want to summarize it. You might wonder, why do we want to do this? Because papers already have abstracts. But it turns out that abstracts are not always the best summary, and sometimes are flawed. I'm going to go to reasons why it is that the case, but in short, abstracts are not always up to date, and sometimes they're missing key contributions of the paper. So I'm going to talk about an alternative way of summarizing papers, which is complementary to abstracts. And that uses citations. If we have enough citations to a paper, we can get the text surrounding these citations and capture the key contributions of the paper. And I'm going to show how we can improve that using the reference context for the citations. In the second part of the talk, I'm going to talk about some of the real-world challenges with direct impact on human lives. This chart shows leading causes of death in the US. There are a variety of reasons, but two of which are medical errors and mental health and suicide. I'm going to talk about some of the works that we did to take a few steps towards addressing some of the challenges in these areas through NLP. Most of my remaining time, I will talk about mental health, but I'm going to touch on some of other works that we did to address medical errors. So scientific document summarization. This is a summary of our works that have been published in journal and conference venues in NLP and IR. Again, the goal of scientific document summarization is to help researchers keep up to date with the development in their fields. If you want to summarize a long paper into a summary, there are some differences than like summarizing a news article, which is just a few pages. Articles are longer in scientific communities, and therefore when you generate a summary, it has a kind of higher compression rate. And there's some kind of a discourse pattern, a standard discourse pattern that authors use when they first talk about their hypotheses, methods, experiments, findings, and so on. Abstracts are a form of summary. And as I said, they are written by authors, and they include some information about the paper. But it turns out that they're not always updated, especially in biomedical domain. The main contributions of the papers are published in journal venues. And in journals, articles go in rounds and rounds of revisions. And it turns out that authors forget or do not update abstracts many times. And there are some contributions that are not stated in the abstract, or sometimes are overstated or understated. And in our fields, for example, we have space constraints for conferences, and we usually compromise the length of the abstract. And we do not include some important information. So an alternative way is to just use the text surrounding citations. Because each of these citations is capturing some specific point about the paper. If we put them all together, we are able to basically capture different aspects of the paper. This is good because, again, it is written by several people. It can capture various viewpoints. It includes contributions that have real impact because people have talked about it later. And it includes comparison with future work that is not always present when the author is writing a summary. And sometimes they include more details that are more useful to the researchers in that field. But it turns out that they're not always accurate. We all seen citations that talk about, for example, our work or another work that is not what we meant. And they sometimes lack context. For example, they say that this author did this and it resulted in this conclusion. But they do not mention what was the assumptions or conditions under which that results were obtained. And there's another problem that is called inconsistency between degree of certainty of findings, which is a serious problem, especially in biomedical domain. I have an example here. So the reference article on top talks about the possibility of a drug curing a cancer, just a possibility. But when people later on talk about it, they talk about it as if it directly solved that cancer tumor, which is not what the original author meant. So if you take all these and generate the summary of the paper, you will have a summary that is not accurate. So what's the solution? One solution is to consider the context from the reference article. If we have this citation text and find what parts in the reference article are directly about it, we can basically consider them together to prevent those problems. This is an information retrieval problem where we have the citation text, which is the query, and we want to retrieve reference spans from the article that are related to it. The challenges with this problem is that the citations are long and there are variations in the vocabulary usage between the citing author and cited author. So we propose 3 methods to be able to address these problems. First one is query formulation, where we make the query or citation more expressive to be able to better capture these references. In second method, we propose a method based on embeddings and domain knowledge to be able to close the vocabulary differences between the 2 authors. And finally, we take advantage of some labeled data that we have to train a supervised model. So this is the general framework of our query formulation method. We have a reference article that has several textual spans. These can be sentences, a couple of sentences, or part of a sentence. We take them, we index them into a search engine. On the other hand, we have a citing article that talks about this work. In it, there's a citation that we want to find what parts are related to it. We take this citation, we apply query formulation to make it more expressive, and then submit it to a retrieval engine. We use Elasticsearch, which is an open source search engine for this. And we retrieve some initial textual spans. These can contain duplicates or overlap parts, and they're not ranked perfectly. So we apply re-ranking and merging to get final cited spans. So these are the parts from the reference article that are directly related to this citation. In second approach, we propose an information retrieval model that is based on word embeddings and domain knowledge, with the goal to close the gap, vocabulary gap between the citing and cited authors. If you're familiar with language modeling for IR, we have a query which contains of several words. Then the documents are ranked according to this conditional probability, which boils down to the probability of query terms happening in a document. And this directly relates to the frequency of words in the document. People usually use some sort of a smoothing. Here I'm showing Dirichlet smoothing, for example, to be able to solve the cases that this probability is 0. If you want to use this solution for our specific problem, it will not work, because the documents are textual spans that are usually short, and most word frequencies would be 0. So the probability distribution that you will get is not discriminative enough. And also there's this terminology variation problem. So one idea is if we can replace this raw frequency with some sort of semantic frequency, we will be able to address this problem. And we can use word embeddings for this. So I think you're all familiar with word embeddings. They're basically mapping of words to a distributional space so that words that are semantically related to each other are closer to each other. And there are representation learning methods like word-to-vec, glove, and so on that can learn this kind of embeddings. So we replace this frequency with a kind of a semantic frequency that, that basically, the first idea that we can use is just take the similarity between embeddings. This last part shows that. If we take dot products between embeddings, then we can replace that frequency with this and it will work. But unfortunately, it will not, and I will tell you why. So these are words that are trained on word-to-vec and randomly taken from the collection. You can see that some irrelevant words like marker and mint, notebook and the sky, capture and promotion have similarity values that are non-zero. So if you want to consider them into retrieval model, you will get a lot of noise. So we introduced this threshold.
Sorry,
yeah.
Just go back. Again, not to pick on your example, but I agree with you that marker and mint and notebook and sky are very far, but blue and sky and produce and make, which are your highest similarity, are actually, I would argue, would be good retrievals.
Oh, these two, yeah. The last parts are, yeah, those are good.
Separating those two. So, but it's non-zero, but I guess I'm not clear on why this is a problem, right? It doesn't have to be zero, it just has to result in appropriate ranking or separation. And from your example, now that I understand it better, it still looks like it works great.
So the problem is that if you, for example, have a citation that has word capture and then you have, a reference span that has promotion, it will get partial scores. And these partial scores, this one with this one is not discriminative enough. So it introduces a lot of noise.
Because you have a sum over terms and you're more likely to have an irrelevant term.
Yeah, exactly.
A lot of contributions.
Yeah. So I'm going to show you how we can solve this with a threshold and with a transfer function. So this threshold basically sets this irrelevance word to 0. And for this, for setting the threshold, we can get the tail of the distribution of all similarities. And finally, we have to apply some sort of transfer function. If you look at the embedding similarities, this is showing a random word from the collection and top 2,000 words to it. And if you look at the results of similarity values between this word and these words, you can see that they're not discriminative enough. This is not what we want in a retrieval model. In a retrieval model, we want only the top, similar words to have high similarity values and then drop down as we move on. And this transfer function, which is a logit function, gives us this characteristic. So we use this to dampen the effect of less similar words.
So X is the original similarity? What is X?
Oh, X is the similarity value, yeah. So the second extension that we did was using domain knowledge. We know that representation learning can help us capture syntactic and semantic information from data. On the other hand, there are semantic lexicons or knowledge graphs that are built by experts that might include information that are not in embeddings. And research actually shows that they include these information. Especially in biomedical domain, you will have interactions between genes or drug symptom relationships that are captured in expert-created ontologies. So we can utilize these in our model. The first way we can do this is basically by post-processing approach like retrofitting. Retrofitting is a method proposed by Faruqi in 2015 that they take trained embeddings and they try to pull closer to each other the embeddings that are related to each other according to a semantic lexicon. They use WordNet lexicon for this. We take their method and we apply it on two other ontologies. First one is medical subject headings or MESH, and the second one is protein ontology. We use these lexicons, ontologies, because our data set is in biomedical domain. And it includes a lot of interactions between genes and proteins that these can capture. The second way is to directly incorporate this domain knowledge into the probability of words in a document. So the first probability is according to the previous. The second one is related with this one, which basically assigns a partial score to words that are similar to each other but not equal to each other. And finally, we had a small labeled set that says, for example, this citation is related to this reference span. So we could apply a supervised model on this. We use features that are basically about semantic similarity, for example, word match, fuzzy word match, TF-IDF and count-based similarities, and embedding-based similarities. So experiments. We used 2 data sets. First one was NIST TAC dataset. TAC is Text Analysis Conference, which provides test collection and is a NIST-sponsored conference. And second, we also tried this method on another domain to see that if our model is able to generalize to other domains as well. The second one is from computational linguistics papers. The way we evaluate this is using character offset overlaps and sentence overlaps. So if you have a ground truth that's annotated by an expert, and this is our prediction, we basically see what are the positions that we overlap. And finally, we consider Rouge scores, which take the content similarity. I'm going to talk about Rouge a lot in this work. So if you're not familiar with Rouge, Rouge basically compares 2 textual parts by taking n-gram overlaps and longer common subsequence. There are other variations that take like skip grams and so on. This is used for evaluation of summarization. These are the results on TAC dataset. The top part shows baselines and bottom are R methods. QR is query reformulation. You can see that query reformulation using keywords is basically working better than others. Word embedding methods actually are improving over those, and not surprisingly, biomedical trained word embeddings are working better. And incorporating domain knowledge by both ways has positive effect on the results, which is expected because this data set is in biomedical domain. On the this computational linguistic data set, we can see that the results again are higher than baseline usually. And we can see that word embedding models based on Wikipedia are working better. And here retrofitting is not helping that much. And we believe that's the case because in general domain we use WordNet lexicon. And in WordNet we can basically capture general meaning of words, which might not be very useful for computational linguistics papers. They might have specialized concepts that are not captured through this ontology. So if you have a better ontology that is suited for NLP or computational linguistic domain, we might have better results here. A supervised model is working the best in terms of Rouge scores. And what is interesting is that our models are unsupervised, these word embedding methods, and they're able to get better results than supervised one. So why domain knowledge is helping? If you look at a word like expression, we all know what it means, but in terms of biomedical domain, it is related to genes and those things. So if you look at the top relevant words to expression based on embeddings that are trained on Wikipedia, you will see that these words are most similar. But in domain specific, if you train it, you will get these which are related to that biomedical domain. And this is exactly what we want. That's why it's helping. And if we look at the features that the supervised model picks up, you can see that features like character n-gram TF-IDF similarity and embedding-based features are helpful. And interestingly, count-based similarity and word match features are not very helpful. So to summarize, we showed that how we can add context to these citations. Now we want to use them to summarize papers. How we can do this, I will talk about this. So this was an extractive method for summarization, which basically takes advantage of the context of the citations in the paper. It includes 4 steps. It's a kind of pipeline approach. I talked about the first one, which is extracting this context. Then after we extract them, we group them together. Then we rank the sentences within each group based on their importance. And finally, we select sentences for the final summary. So Yeah.
Sorry to interrupt, but just
Sure.
we do a lot of work on information extraction here. Just
Sure.
so people know, extractive summarization has nothing to do with that.
Oh, okay. Yeah.
It's a term from the field of summarization.
Yeah, exactly. So we have two methods for summarization. First one is extractive, where you pick the sentences, and the other one is abstractive, where you generate the summary from scratch. So this is the first method. Thanks. So community detection is the first method for grouping citations. Let's say that we have this graph that shows the relevance of sentences to each other. Nodes are sentences, and edges are weighted similarities between them. We want to find subgraphs that are related to each other, but not related to other subgraphs. This can be captured by using a quantity called modularity. And we can do this by using a hierarchical bottom-up approach by maximizing this modularity. This results in subgraphs that are densely connected to each other, but not to other subgraphs. And the goal is to put similar citation contexts in similar groups. The second one is using this discourse structure that scientific papers have. If we can relate each citation to what parts the author is talking about, then we can basically capture various aspects of the paper. We do supervised classification for this, where we take features from the citation and the context to be able to do this. So we have these groups. Now we want to find what sentences are important in each of them and select them as representative of each group. Let's say that these are the groups. Then in order to find most important sentences, we use the centrality notion, which can be captured by a method like power method, which is like a random walk page rank based method. And using this, we can basically rank sentences based on their centrality. And once we have this rank, we can select sentences for our final summary. We do this by two ways. The first one is iterative, where we just pick sentences until we meet the summary threshold. And the second one is a greedy approach, where when we want to add sentence to the summary, we also consider how much novelty it adds to the summary. Experiments are again on TAC dataset and SciSum dataset, and we evaluate this using Rouge framework. These are the results. I'm showing box plots here, which also show the variation of the results between topics. Orange ones are our results, and blue ones are baseline results, and green on left is human score. So we can see that here we are working, our methods are working very well. They're outperforming all the baselines, and in one term, we're specifically matching the human score as well. So the left on your right, no, on your left, sorry. It's Rouge 1 scores, and this is Rouge L scores. And we can see that these are 100-word summaries. If you move on to longer summaries, we can see that still our methods are working well. But they're not working as well as human. And we looked at the summaries that we generate, and it seems that when you move on like 250-word summaries, there's some nuances that human can capture, whereas extractive methods cannot capture. And if you look at results for citation summary, which basically takes the citation themselves, you can see that it's not working very well, which confirms our initial hypothesis that citation-based summarization using only citations might not be accurate.
So you're evaluating this by Rouge score, which is overlap of sentences from the reference paper, right? The citing paper. So how is there any overlap between the citation context and that?
So this is overlapping of the final generated summary with the human generated summary. These are summaries. Yeah, previous part was just, so first.
So you're comparing against a human generated text, which is independent, not extracted.
Yeah, exactly.
Do you have like a baseline that uses just the abstract of the paper and summary compared to the human summary?
So the human summaries that we had for this task considered both the citation and the content of the paper. So they wanted to kind of generate a blended summary that takes advantage of the two. If you only compare to abstract, I suspect that the results would be lower because those are kind of different. They only consider the content of the paper, but we didn't compare.
So the human score is one human summary against the second human summary?
Yeah, there are 4 human. We take 1 against the 3 and then average them. Okay. So we had these different contextualization methods that we extract from the paper. We wanted to know what's their effect on the final generated summary. Comparing with baselines, they're all working better. In terms of some data set especially, we can see that query reformulation method based on noun phrases is working better. And in tag data set, we can see that, again, the results are positive. And not surprisingly, the domain method is gaining the most increase in the results. So we wanted to know if discourse facets are really helpful or not. So we removed them and we added them again. And in both cases, we see a significant increase in the Rouge scores of the final summary, especially in the some data set that we get about 10 points Rouge 2 score improvement. So to recap this part, I showed how we can use context to make citations more expressive and more rich. And I showed how we can use them to summarize papers. I have other works in summarization where we improve summarization evaluation by metric we call SERA, but I don't have time to go through them. But please ask me offline if you're interested. I'm also working on abstractive summarization, but that's an ongoing process. So are there any quick questions before I move on to the second part?
Both in the abstractive summarization and the previous work, you're actually looking for spans in the original text, right?
Yes.
So what's the motivation of using root score? You're just matching spans, right, from what your method is predicting versus what's the goal data?
Oh, okay. So good question. We might find one part in the paper that is different than human annotation. But papers usually repeat some part. For example, in introduction, we might talk about method. So our method might find some sentence in the introduction that is about method, but the annotator has, identified that part in the method. So we also consider the similarities to allow partial reward for methods.
I'm not sure this is a good question. So, so your how complex are the pipelines of the baseline compared to your method, broadly speaking?
So the baselines usually use supervised methods. So they have, this data set contains a limited set of annotations, about like 300 or 400 cases. So they usually use various similarity, semantic similarity-based methods to be able to generate these contexts. And then they use, different methods to put this together. Most of them use like heuristic methods for generating the final summary after they extract the things. So this part is, again, a summary of several works. I'm going to focus mostly on mental health because of the time constraints, but I'm going to quickly talk about other works that I've done on, clinical reports. So text categorization is a fundamental task in health-related data that helps us better understand these data, summarize them, and analyze them or search them. And it can help promote, healthcare in general. So first part, I'm going to talk about mental health and social media. This is a summary of 2 works. First one was a journal, comprehensive journal publication in IR, and the second one was published in EM/NLP this year and awarded the best long paper. So mental health is a challenge, and although it's a serious problem, many times it is taken for granted. On the extreme side of mental health, there's suicide and self-harm, which is leading cause of death in the world. Around 43,000 people die in US due to suicide, and 500,000 people refer to hospitals for self-harm injuries. So what can we do through NLP to, kind of help this situation? Mental health has a unique connection to language. And there's always a stigma associated with mental health, which might prevent people to go and seek support in physical, world. And social media is always available. So many times we see users that use this social media anonymously to express their feelings or ask for support. Therefore, social media presents an opportunity for us to be able to observe behavior. We want to be able to answer questions like, can we tell someone is depressed without them saying that they're depressed? Or can we tell someone is at risk of self-harm? It has obvious clinical and scientific applications. For example, we can prevent suicide, or we can provide help for people that are depressed. So we can observe this behavior through online communities or forums. There are two types of forums. First one are mental health related, which are specific forums, and the second one are general forums that all people participate in. So in a specific forum, first I'm going to talk about the specific forums and then switch to general forums. They look like this. They're basically support forums that are designed for providing support for people with mental health. In them, there are moderators whose role is to identify users who are at risk of self-harm and talk to them and provide support. If you look at the posts in this kind of forums, you will see that they look like this. On the left side, for example, I'm having bad thoughts about ending my life. Nothing helps. It shows that user is at risk. But on the right side, it's kind of a usual content, doesn't show any risk. So we want to be able to prioritize them, to be able to identify whether the user is at risk or not. And this can help moderators focus their attention on users that are in risk.
Sorry, how did you guys determine which ones were at risk? Like, how did you know that the yellow one was yellow?
These are annotated by domain experts. Yeah, so yeah, I'm not expert in mental health. So we propose a machine learning classifier for this with features to capture post content, context in the discussion, and user state of the mind. For capturing post content, we use bag of words representation, which is a standard, then sentence representation by skip dot vectors, and topic modeling features. Then we captured how the user is feeling by using psycholinguistic lexicons, emotion lexicons, and subjectivity lexicons. And we also considered the context in the discussion, because these are discussion-centric forums. One interesting feature is the last sentence that we saw. In many posts, we see that the user is talking about some normal stuff, but at the end, they might change their tone and talk about something that is severe. For example, here you can see that at the end, user talks about something that shows that they're at risk. So we consider this as a separate feature. Some metadata standard features that we use, like number of views, kudos, which are likes, or time of the day. We also considered an ensemble model whose role is to capture various aspects of these models. So we had data from Reach Out forums, which is a huge forum in Australia about mental health, and they had 1,200 posts that were labeled by expert human. These are results compared with other methods. We can see that our methods, the Ensemble model, is working the best with 20% improvement over the next best baseline, and even the single model is here working well. Instead of all these risk categories, if you only consider binary categories, flag means all the risk categories, and urgent means two of the most severe ones. You can see that again, our model is working better with about 10% improvement. And these are the features. We can see that contextual features, last sentence, and topic modeling features are helpful. So we had this classifier that was working with about 75% F1 score and 90% over urgent and flag categories. We wanted to see if we can do something interesting with this over the entire data set to learn about these users. I should mention that flag, the score is higher because we had more data in the flag category than urgent. So we studied the trend line of content severity, and we wanted to know on average whether this trend line is negative or positive to see how the users feel over time when they interact with the forum. We first filter out users that essentially have flat zero line, flat or near zero trend. And this is because they're moderators or users who show consistent behavior. They can introduce noise to the model, so we remove them. We use different thresholds for this, and we can see that no matter what threshold we use, the average slope is always negative, which is showing that, okay, the users tend to feel better when they interact with the forum, and they have less content severity. The absolute negative numbers are also higher than positive. So this is backed by previous research, which shows that when people talk about their problems, they feel better, they ask support, they feel better, and so on. This shows the value of this forum. However, we are not drawing any causal relationships, like saying that, okay, these forums are helping users exactly, because we are not controlling for other variables. If you look at moderator response time based on the severity of the models, severity of the posts, you can see that on average it takes 4 hours for the moderators to respond to this post, which is too long because most of the suicides happen within 1 hour of ideation. So 4 hours is just too long. We need to, this shows that this task is important and we need to prioritize how we allocate resources. So in this work, we stressed this importance and we showed how we can do this. So a system partially based on top features in this work is already implemented in reach out forums and is in use and hopefully helping a lot of people. So I talked about specific forums that are in mental health. Let's zoom out a bit. Can we tell, instead of identifying if a user is at risk of self-harm, now we want to say if the user is depressed at all or not. And we cannot use specific forums for this because most of the users are already depressed when they join that. So we should use general forums, and we want to be able to identify depression. For this, we use something that's called self-reported diagnosis, where the user is claiming they are diagnosed with something like depression. This is not new. People have worked on identifying depression from social media, but what is different in this work is that we want to focus on language patterns, not only keywords. Because in previous work, having keywords like depression usually helps the classifier easily identify the depressed user. So we want to focus on patterns. And the second difference is that we match each user with a realistic number of control users. Based on various estimates, between 5 to 15% of the US population is depressed. So we match each depressed user with 12 control users to be able to have a realistic data set. So our method looks for signals across users' posts and then merge them to classify the user. More concretely, this is our method. We have several inputs, which are user posts. We pass them through a convolutional layer to be able to extract the signals that identify, the user might be depressed or not. We merge these signals together, and then finally we classify the user. For example, we might have 2 posts. We have CNNs with filter 3. Some engrams might have a higher effect, like don't even feel, but even feel like might not be as important, and so on. We merge these signals by average pooling, and then we merge all of them together with another CNN. So I'll get to the results in a second, but before that, I'm going to talk about the data set that we use. We call this Reddit self-reported diagnosis data set, and the idea, yeah.
So just to be clear, you're convolving over the words instead of using like a recurring network?
Yes, correct. We use convolution instead of recurring.
And then you're convolving again over the post?
Yeah, so we do one convolution for the post and one convolution over the entire post for the user. So the idea is to use self-reported diagnosis to be able to identify users. And the data set is ready. We are finalizing an agreement that protects these users. Although the posts are public, but mental health is sensitive, and to be able to protect users, we are requiring researchers not to contact users or not to make any attempts to de-anonymize them or link them to other social media. So the way we built this data set is like this. We have a user that has multiple posts. We have some high precision inclusion patterns. For example, I was diagnosed with depression, my doctor diagnosed me, and so on. If a user has this kind of a post that shows this, we assume that they have been diagnosed with depression at some point. But we annotate that post to confirm it's actually a self-reported diagnosis. Because there are some false positives, like it's not like I've been diagnosed with depression. So we get rid of these with crowdsourcing. And then after we label our user, we remove every post that is about depression. And the idea is that we want to have a data set to be able to identify users that are depressed by their general language, not a specific language. So we have some exclusion patterns like depression diagnosis and so on that we can filter out the posts that include these. And we also remove every post that user has in mental health related subforums. So for selecting the control users, we first check if they have any posts in mental health related subforums or not. And then we also check if they have any posts that has this exclusion patterns. Then they are a candidate control user. To make the problem more realistic, we match every candidate user to every candidate control user with depressed user based on their post distribution. Because we don't want the classifier to be easily distinguishing these two based on the different topics that they're interested in. So this results in about 9,000 diagnosed users and 112,000 control users, which is a much larger data set than others, and it is much more realistic. So we have two models. First one is CNN-E, which takes the earliest post of the user. This performs roughly similar to taking their last post. And then we have CNN-R, which randomly takes users' posts. We take 400 posts for CNN-E and 1,500, which were chosen empirically. And in both cases, we limit the post length to 100 words. You can see that about 60% of the users have 100 posts or fewer, and about 80% of the users have 1,500 posts and fewer. These are the results we compared with standard baseline in text classification as well as feature-rich baseline. Feature-rich consider all sorts of features on this task, like psycholinguistic lexicons, emotion lexicons, and so on. We also compare with fast text, which is another baseline for text classification. And you can see that our CNN model performs better than all other methods. Even CNN-E is working a bit better than fast text. So we wanted to know what's happening. We take a look at highest scoring 3 grams in the model. And it picks up a variety of patterns, but not many of them make immediate sense. For example, you might wonder why good at darts might have correlation with being depressed or not. But if you move on to the list, then some patterns appear that make much more sense. However, this is not very interesting because we were hoping that our model is able to pick up general usage, not specific keywords about mental health. So we also removed everything that is about medication, therapy, anxiety, and so on. But our F1 score only dropped by 1%. Shows that our model is kind of robust to keywords, and it's able to pick up language. If you look at the user's top scoring n-grams instead, you can see that some patterns show up that are about general usage of the language. And you can imagine they can be followed by some negative sentiment. For example, my whole can be my whole life, blah, blah, and so on. So this makes sense. In this work, to recap, I showed that how we can construct a data set that is realistic for identifying depressed users. And we propose an approach that is able to pick up these signals along the user's posts. And it is picking up on language usage, not keywords.
Sorry if this is a naive question, but how are you recovering the n-grams from the CNN?
We are considering the weights of the CNN on n-grams. The weights.
The weights.
Yeah. So there are other works in this area that I don't have time to go to, but please ask me if you're interested. First one is identifying errors in healthcare, where we identify critical errors versus non-critical errors, and this is already in use in MedStar Health Hospital, which is a huge hospital in US, and it was patented. The second work, we use attentive recurrent neural nets for identifying patient harm in medical narratives. I've done some work on clinical decision support, where the goal is to retrieve scientific literature given a patient case report, where we reformulate patient cases for this. And I've also done work on temporal information extraction in clinical domain. So to summarize the talk, I first talk about scientific text summarization, how we can use citation context to produce better summaries. And in the second part, I talked about health-related text categorization, mostly on social media and mental health. These are the publications. I had time to go through half of them almost, so if you have questions about others, please ask me. Thank you.